Wait, isn't the complement like a completely different binary number though? Well, if you think about it, that formula that we applied, that we mentioned before, it still works. So if you have n your number and b is 2, then you do this b to the power of n minus y, and you get exactly their negation, right? You flip the sign. So if you try this, and for practical purposes, you can think, how do I get -2 from 2? Well, I invert all bits and then I add one least significant bit. Okay, so from 0, 0, 1, 0, I do 1, 1, 0, 1, and then I add 1, and that's how I get 1, 1, 1, 0, right? So we can try a few examples here. So we have 0, 0, 1, 0, and then first I invert all bits, so we get 1, 1, 0, 1, okay, after inversion. And then when I add one bit lower, one least significant bit, what I get is, so 1 and 1, we can do addition using our grade school algorithm on binary and hexadecimal too. So 1 and 1 is 1, 0. So we put 0 here and 1 is carried over. So 1 is carried over. So now we do 0, 0, and 1. It's 1. And of course, here we have two ones, right? And that's exactly -2. So in signed integers, should 8 be represented as this? Let me grab it. So it depends on how many bits you use, right? So if you use 5 bits, then 0, 1, 2, 3, this is the correct representation for 8. Okay, and 0, 1, 2, 3, I was just counting the exponents, right? So this has the weight of 2 to the 0th, 2 to the 1st, 2 to the 2nd, and 2 to the 3rd. 2 to the 3rd is 8, so I was just checking myself, right? With 5 bits, yes, that would be 8. If I told you that you need to have 8 bits, you would do this, right? And quite often we put a space here just to make it easier to count the groups of digits, right? It has no significance for the computer, but for humans, it's common to put a space to make it easier to count. Do the exponents in floats use 2's complement as well? Specifically, excellent question. All right. So yeah, I almost forgot. Another reason I was talking about all the different ways to represent sign is that actually when we get to floating point numbers, you will see that the sign is actually a single bit on its own, right? So it's not a 2's complement notation. And we will talk about it later on. Yeah, we will go over IEEE 754 standard in very fine detail. So, and you will have plenty of opportunities to convert floating point numbers. And it's, of course, a lot more complicated because there are more components, right? There's sign, there's magnitude, and there's exponent. And the exponent is not stored, in a straightforward way. It's stored as a number minus offset. So it's a lot of fun. But yeah, I actually think it is fun. So hopefully you agree. All right, so it's coming up. All right, so that's another great question. So what is this, right? So if I just give you these 4 bits and I ask you what is the value of this binary number, the correct answer is you didn't give us enough information to tell that, to say that, right? To determine that, because you have to know what those bits represent. Do they represent a character? Do they represent a number? If a number, what kind of number? Floating point, integer, signed, unsigned, right? If you do not know this, and if you're not given context, you cannot tell. So if you somehow have to be able to deduce it. Like remember our lab, one lab ago, lab 2, when you could just observe the pattern because we had multiple values in the same file, and then you could make an educated guess of what values were actually written to that file. So if I just give you that number and tell you that it's a 4-bit signed integer, then you treat it as 2's complement, right? So how do you convert it? So what would be their exponents? 0. All right, let me space it out, right, so that we can. So the exponent of this would be 2 to the 0. The exponent of this would be 2 to the first. The exponent of this would be 2 to the second. And the exponent of this would be negative 2 to the third. Okay, so and now given that you can convert. So it would be negative 8, right? Negative 2 to the third times 1 plus 4 plus 2, right? Check my math. So I hope I'm not messing up, but it never hurts to check. Just stay on your toes. All right, so it's negative 6. If I tell you that the exact same bit combination is a 4-bit unsigned integer, right? Then your weights would be different, right? It's all subject to interpretation. So your weights would be, this one would be 2 to the third, okay? And then the value would be 8 plus 4 plus 2, so it would be indeed 14. See how it matters what the interpretation is. All right? And then if I tell you that it's a character, then of course it makes no sense to add any anything, because it's just not a number. All right. And one important thing, sign extension. Okay, so what if I tell you that this, right? So you're given this value, and it's a 4-bit signed integer, and you want to represent it, and I am asking you to convert it to an 8-bit signed integer. How do you do that? Well, it turns out that the answer is very easy. You take the original bit sequence and you extend the sign bit. It can be 0, it can be 1. Okay, so it's not, you do not always extend 0 or 1, but you extend whatever the sign bit is. It's, in this case, is 1, so just 4 ones here, and you got an 8-bit integer, signed integer, with the same value. It is negative 6. How can you double check yourself? Well, you just count the weights. 0, 1, 2, 3, 4, 5, 6, and negative 2 to the 7th. So it should be negative 2 to the 7th plus 2 to the 6th plus 2 to the 5th plus 2 to the 4th plus 2 to the 3rd plus 2 the 2nd plus 2 to the 1st, and that's it. Okay, so that should all sum up to negative 6. You see how this whole system works, right? The weight of the leftmost bit, which we call sign bit, but it's not just a simple, negative or positive. It has this large negative weight. So the largest by absolute value negative value would be when we have this leftmost bit set and all others are 0. And we can see it exactly here, right? Negative 8, that's the largest negative value in this case of 4 bits. And we see that that's the largest negative value. If this bit is set, then we get this, this large negative value that we can only make less negative if we have some other ones set in our number, right? Because all other weights are positive. So we start with a big negative value, and we are then trying to kind of make it not as negative with those parts. Okay, yeah, it's good. Yeah, starting to make sense. So hopefully things are clicking into place. All right, so this is sign extension, and in contrast, if we say that this is a 4, let's take another number which is not negative. So let's say we take this number, all right, and we want to do sign extension, then we just put 4 zeros here, and obviously the value does not change either. All right. So what is the value? Well, 0, 1, 2. So it's 2 to the second plus 2 to the first. So 4 and 2. It should be 6. Okay. All right. For unsigned, it's trivial. You just extend with a 0. So right, because if we have this as 4-bit unsigned, and I ask you to extend it to 8 bits, you always extend with zeros, all right? Because the weight of this bit for a 4-bit unsigned would be 2 to the third, not negative 2 to the third, right? So you don't want to change the value as you extend, so you always extend with a 0. Okay, and I think by doing those examples, we pretty much covered this thing. So yeah, well, let me go back to my notes. Here are so someone asked about the conversion, right? So you just do the weights, okay? And uh, so here are the examples, right? From binary to decimal, we just assign the we just have to write down the weights and then sum up the weights which are next to ones, right? Because obviously if the digit is 0, it contributes 0 to the number. From decimal to binary, you can do you just follow the same procedure. So you basically have to represent your decimal as a sum of powers of 2. Okay, so if we have I don't know 47, right? How do we represent it? Well, we have to get the largest power of 2, which is less than 47. What would that be? 32, exactly, right? Because the next high would be 64, and it's a positive number. So if we start with 64, there's no way we can make it, down to 47. So we have to start with the largest, but power that is smaller than our number. And so then we have, to add more stuff to make it 47. So we have 15 left, right? So how do we cover 15, right? Well, again, we have to go with powers, right? So we have to do this 15, but it's not a power of 2, so we have to go with 8, all right? And then we have 7 left. So then we have to cover that 7. So we have 7, and 7, we go with 4, okay? And then we still need 3, which is 2 and 1. Okay, so if I got my math right, then it is, let's see, 39, 40. Yeah, I think I messed it up somewhere. Yeah, it's 8 here. Thank you. Okay, so it's 10, 42, and 5, 47. That is, of course, and so it's just 2 to the 5th. So if you have 8 bits, for example, all right, so this is bit with our exponent 7, 6, and then 5, and then 4, we don't have 16, and then 1, we have 8, and then we have 4, and then we have 2, and then we have 1. So it appears that it would be that. Okay. If you notice any mistakes, please let me know. -6 or -2. I'm not sure I caught it. Yeah, please say it again if you noticed a mistake or if I misspoke. That is also possible. Okay, so yeah, basically you represent their value as the sum of powers of 2, and then you just you just put ones in your binary number that are in the positions where you had that corresponding power of 2. All right, and with that, I think we covered this thing, and yeah, so we talked about this most negative, most positive. We had an example, okay, and how the conversion is treated. And signed negation, that's the procedure that we also talked about, right? If you need to convert a positive number to a negative, that's how you do it. You take a complement, you invert all bits, and you add 1. It's not actually 1, it is one of their least significant bit. We will see that you can actually do fractional numbers, fixed point fractional numbers with the same kind of method. It's not going to be a floating point, it's going to be a fixed point, but it's important to see that it's not going to be 1 always. It's 1 in this case just because we have integers. All right, and here's our first pop quiz. Let me open it. Okay, and then we go on. Sign extension, something that we just talked about, right? If you have a number that you represent using so many bits and you want to use more bits, you have to be careful if you're dealing with signed integers, right? Because you would have to extend not 0, but the sign, which in case of negative numbers would be 1. And there are a number of cases when it actually matters in MIPS. There are instructions that extend the immediate value. Add I, you have seen already examples where that immediate value can be negative, right? We were talking about the fact that there is no sub I because we can do add I with a negative value. Okay, so that does matter. And there are also instructions that allow us to load not the entire word from memory, but half a word or even byte. They're useful when you deal with characters. And those instructions are LB load byte, LH load half word. And of course, they also extend their sign, because when you load a byte from memory, it's a byte, but you put it in the register, and the register is always 32 bits, right? You cannot, we don't have half register or quarter of the register. You always load the whole register. And if you only have 1 byte read from memory, you somehow have to fill in the remaining 3/4 of their register value. And you do that, or MIPS does that by extending the sign bit. Half word is 2 bytes. It's 16 bits, and quarter of a word is 1 byte or 8 bits. All right, so that was that. Oh, and we have immediately our second pop quiz. So yeah, I know many of you are close to getting 2 late days, 2 extra late days. All right, so that's poll number 2. And now representing instructions. All instructions that we write in this mnemonic form, right? Mnemonic meaning it's kind of abbreviation, like LW stands for load word. T0 stands for temporary register 0. So those are convenient for humans, but machines can only work with numbers, and therefore all our instructions get translated into codes. Conveniently, each MIPS instruction is exactly 1 word, one 32-bit word. And if you open your simulator Mars or QSPIM, doesn't matter. You can see that, well, here's some program loaded, and you can see that this is their assembly language instruction that we as humans prefer, but this is actually the machine code for that instruction. And you can see that each machine code is exactly one word. So here is the address, and the address is tracked by a special register called PC program counter. So when a program starts, it starts with this address 0040 and then 4 zeros. And then you see that each subsequent address of their instruction in memory is different by 4 because remember our memory is byte addressable. So next instruction will be at address previous one plus 4, previous one plus 4, right? Because it's 4 bytes, 32 bits. That's why we keep 4, 8, C, and then 10, 14, 18, and so forth. And we have registers. So T0 to T9, S0 to S7, and they are actually mapped to registered numbers. So in the representation, which we'll see shortly, you will see that there's so many bits in their machine code that are dedicated to storing the register number. So hexadecimal, it's pretty straightforward. We just take each group of 4 bits or a nibble, 1/2 of a byte, and give it a short name. And of course, there are 16 possible combinations. So we have that's why we have 16 values here for 4 bits, and we give them letters. We give them hexadecimal letters, hexadecimal because it's 16, from 0 to 9, and then A, B, C, D, E, F. Okay. So that's hexadecimal, and you can easily convert from hexadecimal to binary and back because just using this table, right? So you go from hexadecimal to binary, you take each hexadecimal digit at a time, E, and replace it with the 4 bits from the table. And if you need to go the opposite direction, you just take the 4 bits and replace them with a letter. So that is a hexadecimal, and as you can see, hexadecimals are everywhere, and all well, you can switch, right? So you can actually ask your IDE to show your values as decimal or even binary, but binary are long and hard to kind of grasp, when they're long values, when there are many bits. And decimal is not very convenient, actually, because you cannot easily do kind of break it into parts or see what binary digits are where in which position. So hex is by far the most common way of representing numbers when you write and debug your your lower level code, your MIPS code, for example. All right. So please make sure you're comfortable with the hexadecimal system. It's everywhere. So for MIPS instructions, that some of them we have seen, they have to be converted to a 32-bit value, right? To a 32-bit instruction. And so if you look at this format, this is the format for R instructions. So R stands for registers. Those are instructions that deal with 3 registers. And one example we have already seen is an add instruction, right? That takes 3 registers, 2 that it adds, and the 3rd where it stores the result. And note that those registers here in this format are given by abbreviation. So OP is the operation code. That's the code that determines the type of their instruction, and it's 6 bits. And then RS and RT are source registers. Those are, for example, for add, those are the values that we are adding. And D is the destination register. It's easy to remember because RD, register for destination, RS is register for source, and T is just next letter in the alphabet after S, right? Because we have to distinguish between one source and the other source. That's how they came up with RS and RT. Shamped, a good one. It's a shift amount. It's 0, 0, all zeros for now. Yeah, this stuff is on the test, right? Everything up to slide 61, as we discussed before. Okay. So for now, it's 0. We will see instructions when it's not 0 in a little while. And funct is the function code. It extends the opcode. So here's an example of R format instruction. You write this instruction, add T0, S1, S2, and that's how it gets translated into the 32-bit code, machine code that I just showed you in QtSpim. Okay. And then we have I instructions. I stands for immediate, and here I, that constant has to be stored. It's an immediate value, so it has to be stored as part of their instruction, and that's why we have 16 bits for it. So definitely it means that our constant can only be if it's assigned value from -2 to the 15th to +2 to the 15th minus 1, right? So there is a limited range for the offset. So if you are trying to, do add I with a value that is outside of the range, it's not going to work. Okay, so that's the format for those instructions, I instructions, and we have already seen how instructions are represented in binary, just like data. So everything related to our program is stored in memory. The program itself, the data, the stack, the heap, those are all parts of the program that reside in memory. And then on top of that, we have logical operations. Hopefully you're familiar with them from C++, maybe. I don't know if that was mentioned in data structures at all. But those arrows, right, greater signs or less signs, they correspond to shift operations. Yeah, bit shifting wasn't mentioned. Okay. We deal with them now. So shift left means that you take their number and you shift all bits to the left. Okay. Yeah, and someone is mentioning that we are flying through the material, but yeah, we have to kind of accelerate a little bit because we are a little bit behind, and hopefully this material is still doable, right? Hopefully you're still able to grasp it. Yeah, someone says no. Well, we are going so fast because we have a pretty dense schedule. Okay, you want me to slow down? Okay, well, let's see where we get and then decide what to do at the end of the lecture, okay? So, I want to keep up with the pace of the class that, and cover the material that we are supposed to cover, but on the same time, of course, I don't want to lose you, all right? Oh, I love that. You mallocing those slides right now. Okay, all right, I'll slow down a bit, okay? Leave MIPS out of the test? No, MIPS still going to be on the test. All right. If anything, we probably, if we don't cover procedures, so be it. We include it in the next test. But this stuff binary logical operations we have to cover, and we still have like half an hour. So I think we're good. Will you accept Fortran on the test? No, not on this one. All right, so shifting means a very simple thing, but a very powerful thing. So suppose you have this binary value, and when you shift it, you specify by how many positions you shift. Let's say 2. Okay, so here I'm assuming that this is binary and this 2 is decimal. Okay. Or I can say it's hexadecimal, right? Makes things, which is of course the same value. So that will mean that I take my bits and shift them all to the left and fill in their vacant positions vacant bits with zeros, right? See how we effectively shifted our bit combination to the left by 2 positions. And if you look at what happens to their actual number, it's multiply by 2 to the power of 2, where 2 is the number of bits we are shifting. Right? We shifted 2 bits. We multiplied by 4, 2 to the second. If we did shift by 4 bits, it would be multiplying by 16, 2 to the fourth. Okay. Yeah, we won't have less than a minute per slide because we already covered many of the slides before slide 61. So we covered that lecture ago and 2 lectures ago. Okay, so that's shift left. Shift right is the same thing. So and as some of you might have guessed, if and by the way, this 0b is a prefix for binary numbers that can be used with some compilers in C. So you can give it a try. Not all compilers support it because it's actually not part of the standard, but many compilers do support it. Okay. But this is only in C, so it's not going to work in MIPS that way, right? In MIPS, go with a hexadecimal. Okay, so and for shift right, let me do a different example. Let me do 0F, and I'm shifting right by 1. Okay, what am I going to do? What am I going to get? F is 4 ones. So if I shift right, I'm going to get 3 ones in binary. And 3 ones is 7. So I'm going to get 0, 7. Okay, so effectively, this is divide by the corresponding power of 2, by 2 to the first, and truncate. So if the result is fractional, we just truncate because we see here we have space only for integers. So if the bit that is been, so we went from this to this, right? So that bit got shifted out. There's no room for it, right? Because we are shifting to the right. So that bit disappeared, and the vacant bit on the left is filled with 0. And it's filled with 0 for a logical shift, right? If we want to treat this as a signed integer, we have to do a different type of a shift, arithmetic shift, because that would preserve the sign. Okay, so it would fill in this position not with 0 but with 1, so that there, our when we divide, the number cannot go from being negative to being positive. Okay, so that's why we would have to fill in with 1, not with 0, for the arithmetic shift. So a logical shift right works correctly only for unsigned. If you want it to work correctly for signed values, you have to use arithmetic shift, and there are instructions in MIPS that do both types of shifts, both their logical and arithmetic. And then there are bitwise operations, and or, not, and XOR. Does shift right arithmetic work for both unsigned and signed? Yes, it does. Except for, you don't want to use it with values that are not numbers, right? So if it's not a number, you probably want a logical shift. If it's a number, whether signed or unsigned, you can totally do arithmetic shift on that. All right, so and or not logical operations, and so you can, here are the rules, the truth table for some of their operations. Well, they're not here, they're not on the slide, but hopefully you're familiar with their and or not. Was it covered in like any of your other classes? No. Okay. Well, let's do it then. It's well, someone says yeah in Fox. Okay. Someone says yes. Someone says no. Okay. Let's do that. So we have. Oh, I do have the truth tables here, right? Not the truth table, but examples. So let's do the truth table, and so that I don't have to type, let me just open you there. Right. So this is the truth table for some of the, well, for all Boolean functions, and we are interested in some of them. So here's and so we are talking about and, or, and XOR are all binary functions. It means they have two arguments, and each argument is a Boolean value, so true or false. So for and, their function yields true only if both operands are true. All other combinations yield false. Or also called exclusive or, also called inclusive or, inclusive or, gives you true only when either of their operands or both operands are true. So why is it called inclusive or? Because it includes the case where both operands are true. And it's very different from our common interpretation of the or in the natural language, right? If I'm asking you, do you want a bagel or cheesesteak, right? It is implied that you cannot say, well, I want a both, right? You are expected to say which one of these two options you want to go, either a bagel or a cheesesteak, but you cannot get both, right? So that's different from from the mathematical definition of or, right? Because this or is inclusive. You can't totally say I want both. And we do have an exclusive or designated by X or, where it's exactly like in the real world, in our natural language, where you can only say I want one of the two, but you cannot say I want both. So if both operands are true, P and Q are both true, X or yields false. Okay, so those are binary operations. And why are they convenient? They are convenient because they allow you to do masking. So what is masking? So imagine you have a bit combination, which is 1 byte of this, and you do AND with what we call a mask. And let's put a mask like that. So what is the result? Well, we only gonna have ones where we have ones in both their number and the mask, the original value and the mask. So the result is going to be this. So you can see that effectively we set their, we cleared all values from the original number where mask had a 0. Okay, so let's actually change it slightly to this, and we see that the result is still this. Okay, so so we see that with this mask, whenever mask has a 0, the result is guaranteed to have a 0. So we had this 1 here in the original number, but in the result we have 0. So we reset, or we clear that 1 here from the original number, right? So and mask is used to clear certain bits, and the bits that we want to be cleared, they have to have, those bits have to have 0 in the mask. So let's take another example and see what OR does to us. So what if we wanted to do an OR? And let me change slightly like that. So for an OR, we are going to have 0, 1, 1, 1, 1, 1, 0, 0. Okay, so you can see that ORing with a mask sets the bits that were 1 in their mask. Okay, so no matter what their original value was, we set their values that had 1. And if there was 1 in the original number, that 1 stays, all right? So 0 doesn't change anything in the OR mask, all right? It just preserves the value of the original number. But whenever we have ones in those bit positions, in the result, it's guaranteed that bits will be set. With AND, you can see it's kind of exactly the opposite. We clear the bits that are zeros in the mask, and we do not touch the values for which AND had, so for which mask had ones, right? So these 4 bits, they are just exactly the same as in the result as they were in the original number, in the number that we applied our mask to. Okay, and then what about XOR? That's the most interesting one, right? For XOR, all right, 0, 0, 0. 1 and 1 is 0. 1, 0, 0, 1, 0, 1. Okay, that's XOR. So you notice a very funny thing. Those bits that are ones in XOR, they cause the bits of the number to which we apply the mask to be inverted. So if you look at what I currently have highlighted, and then you look at the bits here, they are exactly the inverse of each other. So XORing with a mask causes the inversion of the bits for which the mask is 1. So as another example, if you XOR with a mask that has all ones, we do it carefully, so it's 1, 0, 1, 0, 0, 1, 1, 0. So you see that we just inverted the number that to which we were applying our mask. Okay, so that was that. And now we have another pop quiz. So you can go back to it. So I believe this is number 3. Okay. And then shift operations. We are continuing with our conversation about format for instructions in MIPS. So if we have a shift operation, it follows the R format instruction of R format for instructions, but it uses that stamped flag, all right, or shift amount. So this 5-bit field stamped encodes how many positions to shift. And from this, you can easily say what is the maximum shift amount that you can get with their SLL or SLR instructions in MIPS, right? Because their shift amount is 5 bits. It's always positive. Okay, so it's unsigned. So it's 2 to the 5th. It's 32 positions, which makes sense. So it's not by accident they selected a 5-bit field, because it doesn't make sense to shift more than 32 bits in any direction, because with logical shift you're just going to get a 0. Okay, is that making sense? Like if I demonstrate it on a smaller example with 1 1 0 1, and so it's 4 bits, and if I shift it by 4 positions, I'm going to get 0, right? Because all my bits, even if they're all ones or whatever, they're gonna disappear. They're gonna be shifted out of my bit positions and filled in with zeros. Okay, that's why shamped is 5 bits, because we only want to shift by 32 bits, no more. All right, so that's that. And AND operations we just talked about, right? So it's convenient to use AND or and XOR to mask bits in a word. So here with AND, we clear certain bits, and we just keep the others intact, as this example shows, right? So in this case, T2 is the mask, all right, because we do T1 and T2, and the result is stored in T0. So we see how we cleared all bits except for bits that are ones in T1 in our mask, and for those bits we just kept them intact from T2, right? So you can see if we draw this just as another example. So these bits come here, right? Because we have 4 ones here, and all the other bits are cleared. You see here we had ones, and here they turned into zeros, right? We cleared those bits. Okay, and then we have a pop quiz, yet another one. Okay, on masks, and then all operations we also just talked about. So it's the same idea of masking, all right, or applying a mask, but it's different because here's our mask, and we set those bits regardless of what they were in there, in here, right? So we ignore what was here, and the net result is that we set those bits to 1, and where our mask had zeros, like here and here. Yeah, I'm not doing a good job with my circling, right? So those bits are intact, and that's why we see that those bits, they just came here, and those bits, of course, they just intact. They're not changed. All right, not operations is just the inversion, changing 0 to 1, 1 to 0. MIPS does not have a dedicated not operator, but it has an OR, which is not OR. And we can use NOR to emulate not, right? Because if we use as one of the operands, so not is a unary operation, it only takes one operand, but we can use NOR with a 0. That's another use for our 0 register. So if we OR with 0, it doesn't change their value of their second operand. So A or 0 is A always. And then we apply not to the result. So effectively, we are doing not A in this case. Yeah, MIPS doesn't need to have this instruction. It would be extraneous. We just, we can totally use not to do our NOR. We can totally use NOR to do our not. All right, and here is another pop quiz for you. Yeah, poll number 3 is whack. It asks 2 questions. You only have to answer one. The second one is just basically to entertain you and, to, which one was that? Yeah. What about n Boolean variables? You can actually answer it in the chat. If you have, if you have thoughts about it, please share. Right. So it's not one of the options. Yep. And yeah. So we yeah, it's actually, yeah, you're getting close, but not exactly. And if you want a hint, it's actually here. So how many Boolean functions of 2 operands do we have? All right, here they list all of them. How many of them are? Right, we only discussed a few, XOR and OR, but there are more. All right, so how many of them are here? And then that hopefully helps you get the formula. Okay. Yeah. So someone got it. Yeah. It's 2 to the power of 2 to the power of n. Exactly. Okay. And yeah, by the way, you will get into some of those other Boolean functions in some other courses. So I think in Fox you talk about implication. So that's this thing here. Okay. And if when you take psoft, they will torture you with even more implications. So just get used to this yet another Boolean function of 2 arguments implication. It's pretty useful. Okay, and so then we were here and here. Oh yeah, so we have 2 more calls right here. Okay, so there are 3 calls in a row. So one is to clear certain bits, another one is to set certain bits, and the third one is to invert certain bits. Okay? And conditional operations, I believe we have already covered, right? BQ and BNU a couple lectures ago, and compelling if statements and loops, and basic blocks, and this. So I think we went over this kind of quickly. So let me spend a little more time on those. Right. So here the basic conditional instructions that we have is BEQ and BNE. They kind of very similar, right? BEQ again, let those mnemonics talk to you, right? Understand what they mean. BEQ means branch if equal. BNE stands for branch if not equal. Okay, and so they only test this, right? So no less than, no greater than, just these 2 instructions. That's all we got. And in many cases, they are sufficient. So here's an example. But what if we want a less than or greater than? In this case, we have to use additional instructions. SLT, set less than. So this instruction sets register D, this register, to 1 if the condition is true. And the condition is less than. Who is less than who? Or who is less than whom? RS is less than RT. So this instruction compares RS and RT, which is the second and third arguments. And if the second is less than third, then it sets the first argument register to 1. So this is exactly the pseudocode for what this instruction does. Okay? And you can also do SLT with an immediate value, hence SLTI with a constant. Okay, works the same way, except for you only have 2 registers. One is compared to a constant, and another is set to 1 or set to 0. So if you want to do your less than, you can you have to use a combination of SLT and BNE or BEQ. Okay, so the way it works, if S1 is less than S2, then T0 will be set to 1. So when you execute the following instruction, B and E, you compare T0 with 0. But you know that if S1 was less than S2, T0 would be 1. 1 is not equal to 0. So you will go to this label L if S1 is less than S2, because T1 in this case would be 1. 1 is not equal to 0, and we jump to L. All right, and so that this slide basically explains why why there are no dedicated single instructions for branch less than equal, branch greater than equal, and it's again because of the design principle that B and E, BQ are the most common case, and that's why we want a single instruction for those most common cases, and for cases when we have to branch if less than or less than or greater than or greater than or equal, it's okay to have 2 instructions. As we see in this case, right? It's less common case, so it will take 2 instructions to do this, right? Because we are trying to optimize for the most common case. Can we use pseudo instructions in the exam tomorrow? Yes. And All right, so we have about 7 minutes left, and okay, we have procedure calling, and I kind of sense that you don't really want me to rush. So why don't we leave procedure calling for the next exam? So I think we have enough material for our exam tomorrow. So we save procedure calling for the next one. Okay. So yeah, please then adjust the practice exam problems and solutions, and kind of ignore the ones that ask you to write, or call a procedure or anything along those lines. Will there be shell scripting on this test? No, I think I answered this question. Someone was asking about Unix stuff. So exam 3 is up to slide 43. That is correct. Yeah. So signed versus unsigned. It's just this last slide related to conditionals. SLT, SLTI are signed. If you want to do perform unsigned comparison, you have to use different instructions that have you um, in the name. So it's signed, it's set less than for unsigned, and set less than unsigned with an immediate. Okay, so that was that, and yeah, I'm glad you liked it. Yeah, thank you, folks. And so then for the poll question, someone was having trouble understanding what the poll was asking. I don't know. Did anyone answer and help that person, or are there multiple people who are having trouble with the poll? Still waiting on exam regrade for exam 1. Oh, okay. Those should have been out for exam 1. They should have been out. They should have been done. So please, when you go to your grade inquiry, you should be able to see their grader who graded that question. That would be one of our TAs. Please write them an email saying that you have a grade inquiry from the first exam that hasn't been resolved. It definitely that just an oversight and somehow fell through the cracks. The question of Paul 3 was confusing. Let me see what that question was, and I go to so many Pauls, and okay. Yeah, so basically you are asked to produce this value that later will be used as a mask. So you need to get this value from one of those options, okay? And remember, this is C code, okay? So this is C, okay? So make sure that you interpret the values correctly as far as whether they correspond to hexadecimal, binary, octal, or decimal. Okay, is that making sense? Is it clearer now? Okay. Oh, Paul 3. Paul 3, right here. Okay. Yeah. So it's asking, like, we have functions, Boolean functions. So what does it mean that the function is Boolean? It means that its result is true or false. And this function takes arguments. For a Boolean function, the arguments are also Booleans. How many arguments can we have? Well, we have a lot of variety. We can have a Boolean function that has no arguments. Those would be constant, true, and false. We can have a function that has one argument, like our not Boolean function, right? It just takes one argument. That's why we call it unary. We can also have functions that have two arguments, two Boolean variables as the arguments, and we call those functions binary because they take two arguments. So, and we looked at some of those functions and or XOR, NOR is another one that we mentioned. So the question is asking how many different functions we can have with 2 arguments if the functions are a Boolean. Well, a set of 2 variables just means we have 2 arguments, right? So the set of arguments is 2 variables. Well, it's 2 variables. The order doesn't really apply here, right? This return value differentiates them. So 2 Boolean functions are different if they have different truth tables. That's the definition. Okay. If the truth tables differ in even 1 row, they are different functions. If they are exactly the same, they're not different functions. They are the same function. All right, and so let me stop sharing just for a minute, and we are almost done. But let me see, what was the last poll that I had prepared for today? Just make sure that. Okay, yeah, that's the one that we will save for our next time. Okay, so hopefully, yeah, and truth tables. We just reviewed them from Wikipedia, right? Those are truth tables. Okay, so you see that and X NOR are different because their truth tables are different. They have different values. All right, so it's 1:50, and our lecture is over. Hopefully, I answered at least some of the most burning questions. And if you have more questions, please ask on the forum. Please practice with the practice problems. I promise it's going to help you on this upcoming exam if you practice with the practice problems. And good luck on your exam tomorrow. Please remember, show up for your lab review lecture tomorrow. Torture, in a good sense, our TAs and mentors. Ask them plenty of questions. They are there to answer them. Yeah, good luck and enjoy the rest of your day. Have a good day, and I'm looking forward to seeing you all again on Friday. Have a good one, folks. Take care.